What's up, baby? Shoot. All right. Hopefully you watched the first video. If you haven't watched that first video about the conceptual part before you jump to the calculation part of colligative properties, thank y'all. If you're watching, if you're trying to learn here, that's super encouraging to me. So if you've dialed into this video and you're trying to do the colligative property calculations, you have made education a priority, and so it means a lot to me. So anyway, here we go. These are the calculation half. We talked about freezing point, depression, boiling point elevation in the last little video, and so this guy is how do you exactly calculate the change of the temperature that's going to occur when you add some kind of solute to some kind of solvent. So here's our formula. Real simple formula. Change in temperature equals a constant. I'll show you where that constant is in a second. Out of textbook, I've also attached the constant page to Google Classroom so you can see it there. That's your italic M, that's your molality, moles of solute over kilograms of solvent, and then N is the number of particles that the solute dissociates into. So this is looking back at dissociations when we did net ionic equations. And so constant times molality times times the number of particles things dissociate into will tell us our change in temperature. The number of particles are coming from whether the things are electrolytes or non-electrolytes. So we've talked about this before. If you have covalently bonded things, they don't dissociate into ions. So if we have sugar that we're putting in a solution, it stays as one piece of sugar. It doesn't break apart into lots of carbons and hydrogens and oxygens. Electrolytes, however, and you'll see one of these in the second problem I do here, the electrolytes will dissociate in their ions. So it's not about what you put in, it's how much you put in. If you use something that's an electrolyte, it's going to break apart into multiple particles, and so as a result you're going to get a much bigger freezing point depression or boiling point elevation. It says 2 or more particles. The max you're going to see from me is 5. You'll never see more than 5 particles for me. So if you look at it and you're like, I got 27 particles, it's probably because it's a non-electrolyte thing that doesn't break apart into all those. But 5 would be the most, and they've got to be ionic in order to dissociate that way. So I'm going to show you a couple little calculations here. They're not terribly difficult. There's nothing new here. It's just piecing together stuff we've already done. So here's our first calculation. It says at what temperature will a solution that is composed of 0.73 moles of glucose and 225 grams of phenol boil. So we've got some solute, some glucose. Glucose, you guys know from bio, C6H12O6. It's going to dissolve in 225 grams of phenol. You don't have to know what the solvent's formula is. I'm going to show you on the formula sheet in a second where that comes from. So here we go. So it's change in temperature all the time on these guys. So change in temperature equals K, a constant, times M the molality times N. So I've attached a chart. The chart, if you have an old blue book, is in page 438. If you have the online book, it's 432, so you can see the chart there. Or you can pause the video right there and come back and look at it. And these are our values. So we have 4 columns here. Normal freezing point column for all these different solvents. And then the freezing point constant, that's your K value. If it's freezing, FP means freezing point. And then you have normal boiling point and molal boiling point constant. And so when we look at this, the solvent that we're dealing with in this particular problem is phenol. And so we are dealing with phenol and we are dealing with boiling point. So we look at our chart, we find phenol. That's the normal boiling point. That's not what we want yet. We want the boiling point constant. So there's our K value, the 3.60. Units are degrees Celsius over molal. So 3.60 for our constant. Then we need our molality. So molality, moles of solute over kilograms of solvent. And these sweet angels, they gave us the moles of the solute, 0.73 moles of glucose. And they gave us grams of the phenol. And so this grams of phenol we need to change to kilograms. You should all know how to do that without showing a setup, as far as turning 225 grams into 0.225 kilograms. And then we can solve for our molality. And that's what we get for our molality of the glucose in that phenol solvent. And so that's our second piece. So its change in temperature is 3.6 times the 3.2 molals, all times our N value, the number of particles, which I showed you. This is glucose, C6H12O6. You've got to look and go, is that ionic or covalent? In this case, that's all nonmetals. So a good indicator it's covalent. And so this guy's covalent, which means it's not going to break apart into multiple particles. So our N value here will just be 1. For every 1 sugar we put in, we get 1 sugar out. And so our change in temperature, we're going to multiply those values together. I'm going to peek at the answer. I'm going to cheat so I don't have to plug it in. And our change in temperature here is 12 degrees Celsius. When I look up at the question in the problem here, it says what temperature will phenol boil. This is not, that 12 degrees is not the boiling point of phenol. That is the change in the boiling point of phenol. So how in the world do we know what temperature phenol boils at? You're back to the little reference chart. And so for phenol, the normal boiling point, 181.8. And so our temperature of boiling, our new boiling point would equal the 181.8 plus the 12 degrees Celsius, and that would give us our new boiling point of 194 degrees Celsius. So there's our new boiling point of phenol. There's kind of a quick snippet. You can see their work. So you can pause that if you need to and look back at where those numbers come from. One more? No mas. One more calculation for me. Same kind of idea, a little tweak on this guy. Find the freezing point of a saturated solution of sodium chloride containing 28 grams of sodium chloride and 100 mils of water. So this is practical stuff. You know what water is, you know what salt is, and so we're going to take 28 grams of salt, we're going to throw a bunch of salt into some water, and we're going to see how the freezing point's adjusted. We expect that when we add something to that water, that's what a colligative property is, that the freezing point will now lower. So you start in the same place. Delta T, change in temperature equals K times molality times the N value. And so one at a time, we kill them one at a time. Here we go. The K value is a constant from the chart. Here we're dealing with water as our solvent, and we are looking for the freezing point constant. So there's water. There's the normal freezing point of water. We want the freezing point constant of water. I think you can see it. There's negative 1.86. And so that's where we're getting our K value from. Negative 1.86 degrees Celsius per molal. Good? That's it. The second piece is the molality. So we have 28 grams of sodium chloride. They weren't as nice, this problem. You got to turn that into moles. We need moles of that in kilograms of the water. So our molality, moles of salt over kilograms of water. They gave us our grams of salt. We turned them into moles. 28 grams divided by that 58.5 grams of sodium chloride from the periodic table. And it gives us our number of moles. Don't get too excited. People get the number of moles and then they take that number of moles and they turn it right into, and they put it right in for molality. Be careful. The number of moles here is 0.48 moles of sodium chloride. That is our top value for our molality. We still have to take this thing and divide it by the kilograms of water. They give us 100 mils. This is a conversion we've talked about before, where the density of water is 1 gram per milliliter, which means 100 milliliters is exactly equal to 100 gram. 1 gram of water equals 1 milliliter of water. And so that 100 milliliters is 100 grams, and 100 grams should be 0.1 kilograms of water. And so that's going to give us our molality. It should be 4.8 molals for that salt solution in the water. And so that's our second value here. 4.8 moles. And now we're looking for our N value. The N value is the number of particles that the solute dissociates into. So sodium chloride is ionic. And so when you drop it into water, the water comes in and separates those two ions, and we end up having sodium ions and chloride ions produced. And so for every one of these we put in, we should get 2 particles out. So our N value there is going to be 2. And so our change in temperature is going to be those 3 things multiplied together, and we get roughly negative 18 degrees Celsius for our change in temperature. Now, is that the new freezing point of water? It's a trick question, because the normal freezing point of water is 0, and so 0 plus the negative 18 means our water solution is now negative 18 degrees Celsius. That's the new freezing point of water. So water can get all the way down to negative 18 Celsius, multiply it by 2, add 32. We're talking about negative 4 Fahrenheit without freezing. Pretty incredible. And so that's kind of how colligative properties work there. I encourage you, I've posted a worksheet, I encourage you to get in, try to work through that other worksheet. The data chart I've posted along next to it. See if you can do some problems with this stuff. Very practical. This is something that you'll actually probably run into at some point in your life. Adding some kind of solute to a solvent to make freezing point get smaller or boiling point elevate. I appreciate you watching. If you need anything, shoot me an email. We will talk to you all later.